In universe, there will be no ideal, isn't it? There will be no ideal gases in the universe. So the gases which obeys Boyle's law, Charles' law, Avogadro's law, they are called what? Ideal gases. All gases are real gases only. Only at low temperature and, isn't it? High temperature and low pressure, isn't it? Low pressure and high temperature. Gases can act as ideal, but normally there is no ideal gas. Similarly, what are ideal solutions and what are non-ideal solutions? Yesterday we have discussed the Raoult's law. What is Raoult's law means? The partial pressure of the liquids, the partial pressures of the liquids in a solution are directly proportional to its mole fraction at a given temperature. So if any solution, any liquid-liquid solution, any binary solution, any liquid-liquid solution, which obeys Raoult's law, they are called what? Ideal solution. If they don't obey, they are called what? Non-ideal solution. Very simple definition. Right? Let me discuss about, first of all, the formula. That means definition. Then what happens? We'll see the formula of Raoult's law. Solutions which obeys Raoult's law, isn't it? They are called what? Actually ideal solution. So this they have to obey at any concentration. They have to obey at any concentration and temperature. Condition is what? At any temperature, at any concentration, if they obey Raoult's law, they are called what? Ideal solutions. Right? Next, two liquids A and B. When you mix liquid A and liquid B to form an ideal solution. In this case, the interactions between the A and A and the interactions between the B and B, which are what? C. Which are what? C. Then only they exhibit ideal behaviorality. Understood this concept better? When you are making a solution, when you are making an ideal solution, how you make ideal solution? Whenever two liquids are mixed, A and B, the interactions between the A and the interactions between the B and B, both are actually same. They are having similar attractive forces. Then we can get the ideal solution. I think everyone understood it. In the formation of such solution, to make an ideal solution, what happens? Delta H mix is equal. These are what very important for MCQ questions better. Delta H mixing will be 0. Delta V mixing will be 0. Now, what is the meaning of delta H mixing? And what is the meaning of delta V mixing here? So, first of all, let me see delta H mixing. That means whenever I'm adding liquid A, right, and liquid B, both I'm adding there. Okay. So, to get a solution, here. In this case, heat is neither absorbing nor relieving. Delta H in this process is 0. When you mix these two, you are not getting any type of releasing of energy. Otherwise, for mixing these two, you are not supplying any energy. On its own, they are mixing here. Neither you are supplying any energy to this solution, to this mixture to get this solution, or energy also neither releasing. Understood? I told you one thing here, ammonium chloride. This is actually not here example, but I'm just explaining here. Water. Now we are getting ammonium chloride, what better? Aqueous solution we are going to get. Now in this case, the delta H is equal to positive. Now when you mix ammonium chloride in the water, you get aqueous ammonium chloride solution, the delta H will be positive. And you mix what happened, NaOH in water, right? You are getting aqueous sodium hydroxide in which delta H is equal to negative. That means this process is exothermic, this process is endothermic. But here, for making ideal solution, when you are making ideal solution, the process is neither exothermic nor endothermic. I think you understand. Next, what is delta V here? What is the meaning of delta V here? mixing is equal to 0. Delta V mixing is equal to 0. Now, in this case, what happened? I have mixed what happened here. How much amount I have taken here? I have taken 50 ml I have taken. Right? Here I have taken something what happened? 75 ml I have taken. Right? When you mix these two, the resulting solution will be what? 125 ml. Now, what is delta V? If you observe, delta V mixing is equal to how much we get? Delta V mix is equal to, generally delta V is equal to V final minus V initial. Now, V final how much beta? 120. V initial is what? Initially how much amount you are having? 75 plus 50. Now, is equal to what here? 0. So, when you mix these two liquids, the resulting solution will have same value here. That means the volume neither decreasing nor increasing. Understood better? So delta V mix is equal to 0. Delta H mixing is equal to 0. For which process beta this one? Ideal solution. For ideal solution, this is a very, very important. For ideal solution, delta H mixing is equal to 0. Delta V mixing is equal to 0 here. Next. A perfectly ideal solution is rare. I told you just now, ideal gas equations will not, ideal gases will not be there here. Generally, we have real gases will be there. So here also, perfectly ideal solutions are rare, but some solutions are nearly they act as ideal. Let me see everything. Now, example I've taken. N-hexane, N-heptane, you can take as what? Ideal solution. Now here also one more thing you will get here. Following which examples can be taken as ideal solutions? Which are non-ideal solutions? Following which examples are non-ideal solutions? Then how to identify this one? First thing is that they should have similar chemical properties. The thing is that they should have similar chemical properties. Now tell me hexane and heptane. Which type of hydrocarbons beta there? Which type of hydrocarbons they are? N-hexane and heptane. Yes, which type of hydrocarbons they are? Alkanes, alkenes or alkanes?
Alkanes.
Alkane. Now tell me beta, this one is alkane beta? And this one also alkane. Now alkane and alkane will have similar properties. It doesn't mean that you can take here methane. Can you take like that? No. The molar mass should be near like that. The molar mass also should be near. Not only similar chemical behaviority, the molar mass also should be similar. So hexane C6H, how much beta? 14. Heptane C7H16. They're almost all near molar mass. So you can take this example. N-hexane and heptane is the best example. Now you may get one question. You may get something like that. Sir, methane and ethane, can I take example? Methane, ethane. Is it possible beta? Methane, ethane, can I take? Vaishnavi K. Can I take these two examples? Vaishnavi K. Can I take these two examples? Absent? Vaishnavi K. Vaishnavi VH. Absent. Vanita?
Sir, there is a large difference in their masses.
Can I take these two? Large difference. There is no large difference beta. Only 2. Here also 12 plus carbon is 12. No. Plus what? 2. 14 difference. Here also 14 difference is there. Both are having the molar mass is 14 difference only. Both are having 14 difference only. Both are having difference in CH2 only. Can I take these two examples or not? Yes or no? Only that. Say yes or no.
Yes.
Sir.
Okay. Do or what ideal solutions? Can I take example for these two are ideal solutions or not? Yes or no? These two. Yes or no? I'm not getting any answer. These two are what actually? Gases. Methane is a gas, isn't it? Ethane is a gas. So gases we can't take it. We are discussing about liquids here. Liquid in liquid we are discussing, correct or not? So consider whatever, whenever discussing the examples, what happened, they make you like this also. So in examination, if they give like this also, what we see is both are having same chemical properties and having molecular differences, what only CS2. So we can select this one, but don't select like this because these are gaseous molecules. Understood better what I am saying?
Yes, sir.
Second one is called bromoethane, chloroethane. What difference you are observing? Here it is ethane and here it is ethane. Bromoethane, chloroethane will give their same properties or not? For example, if I take what happens, CH3, CH2, bromine, reacting with aqueous KOH. Reacting with aqueous KOH. Can anybody say what is the product in this case?
CH3 KBr.
KBr. CH3, CH3.
Bromoethane.
What is the product beta? Aqueous KOH if you add.
Ethanol.
Ethanol. CH3, CH2, OH. Here what is the product beta? CH3, CH2, OH. Nucleophilic substitution reaction. SN2 reaction. SN2 reaction. Aqueous KOH. Nucleophile. Substituting what? Nucleophile. So you can take this example, very good example, this one. Bromoethane, chloroethane. These are liquids beta. Ethane is gas. Ethane is gas, but chloroethane is not gas. Benzene and toluene can be taken. How it looks, what happened? Benzene looks like this. This is benzene. And this one is what actually?
So how can we distinguish that it is a gas or a liquid?
The lower molar mass. Based on the lower molar mass. Isn't it? Formaldehyde. Isn't it? Acetaldehyde. Propanaldehyde. See, this is a gas. This is a liquids, isn't it? And if you increase, what happens? One more carbon, that becomes solid. So molar mass increases. When molar mass increases, isn't it? This is also liquid. Now it gets solid. As number of carbons are increasing, so gas converting into liquid, liquid converting into gas, like that. Right?
Yes.
Right. Next, benzene toluene, almost all looks same only. No, benzene toluene, both are benzenes only. Only you are having extra methyl group is there. So they are ideal solutions here. So these are some examples I have taken. The textbook also have same examples. You practice these examples better. What you have to practice now in this one, definition. What is ideal solution? Then delta H is equal to 0, delta V is equal to 0 for mixing. Then what happen? Examples. So next. This is now non-ideal solution. If you know the ideal solution, definitely we can get the non-ideal solution. Just by writing what? Does not obey Raoult's law. By just writing what? Does not obey Raoult's law, we can write that one as a non-ideal solution. Now in the previous case, you written delta H is equal to 0, right? Delta V is equal to 0, but yet not equal to 0, we write it. Okay. So now here, the solution does not obey the Raoult's law at any concentration and temperature is called non-ideal solution. Otherwise, a solution which does not obey the Raoult's law over entire the range of the concentration, at any concentration, okay, at any temperature, it does not obey the ideal solution. Any temperature you take it, not a single temperature, at something what happened, 25 degrees Celsius, it is not obeying what, at entire the range, whatever the temperature you take, whatever the concentration you take, it is not at all obeying the what? Raoult's law. Isn't it? Right. Now what we can take here, delta H is equal to what we can write beta? Not equal to 0. Delta H mix not equal to 0. Delta V mixing not equal to 0. Now in this case, I told you in the last case, AA interactions and BB interactions, both are what happens same. The attractive forces present between AA and BB are what? Same. But in this case, it is not same. The non-ideal solutions are those in which solute-solvent interactions are different than solute-solute and solvent-solvent interactions. So, for example, sorry, I have tried like this. The previous case, I have tried. Just a minute, I will rewrite this one. Here in this case, here, right here. Here, what I have to say here, like this: AA interactions or what BB interactions will equal to what AB interactions. That means whatever the interactions we're having with AA, whatever interactions we're having with BB, which definitely will be attractive forces, same here. That means whatever the attractive force present between A and A, similarly, whatever the attractive forces between B and B is equal to what? A. Okay, for example, two twins are there here. A and A both are twins. Right? BB also both are twins. BB are twins and AA also twins. Now what happened? So these belongs to same home and these two belongs to same. Both are what? Twins only. But because staying at same home, no, so they don't have what they are having same interactions in the same, because they are staying at home. So same interactions they are having. When they meet in ground, what happened? A and B both will make a friendship. Here also A and B both will make a friendship. And whatever the interactions they are having at the home, same interactions they are having when they meet at ground. So no change, nothing is different here. Similarly, what happened before mixing? Before mixing, the interactions between the liquid, same you are having here. For example, you take one more example. I will take what happened here. Benzene. I'm taking here benzene. Here I'm taking what? Toluene actually. Okay. The interactions between the benzene and benzene, and the interaction between the toluene and toluene, if you observe what happened, same interactions we are getting when benzene is mixing with what here? Toluene. Okay. The same interactions, whatever the interactions we are having here, AA interactions or BB interactions, here what happened? AB interactions, all are what same. But in the case of non-ideal solution, what is happening here? In the case of non-ideal solution, the interactions before and after will be different. For example, if you take what happened here, A and A, B and B. When they mix, what happened? They are getting AB. When you mix these two, what happened? You will get AB. Now the attractive force is present here. The interactions are present here, and here will be different. So this type of solutions will be what? Having in non-ideal solutions. Understood better. So what we are saying, solute-solvent interactions. Solute-solvent interaction. That means AB interactions are different when you compare with solute-solute attractions. This is solutes. For example, this you remember is a solute, and this will become solvent. Whichever is high is called solvent. Whichever is low is called solute. Now these interactions are different. Now delta H mixing is not equal to, that means if you mix this one, heat may be released or heat may be absorbed. So when you mix, isn't it, these two liquids, it may be endothermic reaction or it may be exothermic reaction. And when you mix, what happened? The volume change you are getting different. For example, if I mix here, what happened? If I take here 50 ml, if I take here what 75 ml, how much I'm getting? I'm getting maybe what happened less than 125 or maybe greater than 125. But I'm not getting equal to 125. I'm not getting equal to 125. How much I'm getting? Maybe 124 or maybe 126 I'm getting here, but not 125 because the interactions are different. No? For example, just imagine better here, when you compare these interactions are very strong. Just imagine that. In that case, volume will be decreases. It may lead to 124. Otherwise, interactions between these two and compare with this one, if it is having less interactions, this is having less interaction. In this case, what happened? The volume will be increases to what 126. Now, if the vapor pressure of non-ideal solution is high, then exhibit positive deviation. Then what is positive deviation? I will explain in the later slides here. If vapor pressure is low, then exhibit what happened? Negative deviation. This negative and positive we get in detail in the next slides. Now, you have to give the answers now here. Now, I didn't explain that examples here. Non-ideal solution. Whatever the remaining solutions will be non-ideal only, no. Except ideal, remaining will be non-ideal only. In that case, no need what? Examples for non-ideal. Don't search for non-ideal solution examples here. If you get ideal solution examples, remaining will be non-ideal only. Now, anybody? Which pair will not form ideal solution?
Option B. B.
Yes, beta.
B. Option B.
Option B, water and alcohol. Molar mass. But completely different here. Correct or not?
Yes, sir.
Now let me discuss about non-ideal solutions, because we don't have any problem. We are not getting any problem with ideal solution. The problem you're getting with non-ideal solutions here. So let me discuss non-ideal solution with positive and negative deviation. Now solutions with positive deviation. When you get positive deviation, when you get a positive deviation here. Now in these solutions, the solute-solute interactions, A and A interactions, and B and B interactions, if you observe, are stronger than AB interactions. We get a positive deviation. Understood better. But for example, what happens if A and A are attracting more, B also attracting more, but when you mix, what happened? The attractive forces between A and B, what happened? Very less. So solute-solute, solvent-solvent interactions are what? Stronger. This is what? More. These interactions are what? AA is having more interaction compared with what happened? A or BB. Greater if we get positive. Wherever if we get greater than, we'll get positive deviation. Wherever if we get less than, we will get, in this way you can remember here. Right? Positive deviation means always should have greater values. Correct? Right. Next. The partial vapor pressure of each component of the solution is the greater than the vapor pressure as expected according to the Raoult's. According to Raoult's law, what we can write beta? Partial pressure of A plus partial pressure of B is equal to what? P total. Correct or not? If it exhibit, this will be ideal solution. This will be ideal solution. Now here, non-ideal solution with positive deviation is what? Now I can write PA plus PB is always greater than PT. Then we get non-ideal solution with, isn't it, positive deviation. Non-ideal solution with what? Positive deviation. Positive deviation. Wherever you are writing this is equal to what? Or greater than, you have to put what? Greater than for what? Positive deviation. That means the partial pressure of A, for example, you are having 300 atmosphere pressure. Sorry, mm mercury. So just imagine like that. Hypothetical values should take 300, 450. This will be maybe what happened 780 or 760 like that. Sorry, 740 like that. When you observe this one, how much we get? How much we should get? Actually, 750 we should get. But how much we are getting beta? 740. Correct or not? So this is what positive deviation. Similarly, volume also we get same thing. This is pressure I am taking, right? The partial pressure of each component like A and B. Partial pressure of A and partial pressure of B is always greater than the vapor pressure of total vapor pressure here. This one, total vapor pressure. Next, the interactions becomes weaker, hence escaping tendency of molecules increases. So what is the meaning of this one? Let me see here. Now I have taken ethanol and I have taken what? Acetone. Two examples I have taken. Ethanol and acetone. Ethanol is having alcohol beta, alcohol. Whereas acetone is having ketone group beta. So their functional groups are different. Definitely, alcohol will have same type of properties, and acetone will have same properties. That means between the alcohol, the interactions are strong. Between the ketone and ketone, interactions are strong. But when you mix alcohol and ketone, the interactions we are getting weaker here. So what is happening? I'm writing over here like this. Now I've taken here ethanol plus what happened? Ketone. Now we are having some attractive forces between these, right? Now here also some attractive forces are there between alcohol. And here also what happened? Ketone. Now here these attractions are very strong. These are very strong. And these also what? Very strong. But these attractions are very weak here. So what actually it want to do actually now? Ethanol and ketone. Now they will break this one. They will break these interactions and they want to go again into what? Alcohol. Again they want to go what? Into ketone. So what are they saying? a mixture of ethanol and stone shows positive deviation. Okay, why? Because the interactions are becoming weaker. Where here? Hence, their escaping tendency of molecules increase. That means now they are grading. What happened? This bond is getting breaking here, and again, what going to it? There, what initial state here? Initial state is what actually alcohol. Now, where the interactions are stronger here. So, in ethanol, what type of attraction forces will be there? Definitely hydrogen bonding, because ethanol C2H5OH, and what happened? C2H5OH. Now, both these two will have hydrogen bonding. Now, isn't it? See, now for getting these hydrogen bondings here, for this getting these hydrogen bondings, this will be broken here. So what I am saying here, the new bonds which are getting here will be broken and convert into old bonds. Isn't it? For example, what happened if backbench students are there? Backbench students are there. So I have asked the backbench student, isn't it? Example, what happened? We can take backbench. कौन बैठता? Generally आपका क्लास में कौन बैठता है बेटा? बैकबेंच में किरण बैठता है. तो मैंने उसको बोला फ्रंट बेंच में बैठने के लिए बोला, ठीक है ना. मगर मेरे क्लास होने के बाद फिर वापस कहाँ जाते हो? बैक बेंच में जाता है. Similarly, what happened when they mix? What happened? Whatever the interactions are there, that interactions are weak, therefore they will go back into their previous interactions, right? Now in this case, what happened? Delta H mixing definitely will be greater than Z. V also greater than Z. That means definitely it will be endothermic beta. Positive deviation always will be endothermic. Why it is endothermic? Can anybody say? Anybody say what? Why it is endothermic beta? Why it is endothermic? Anybody say? Because whatever the liquid is formed here, solution is formed by A and B, isn't it? You got AB. This is what? Weak bond, correct or not? This is weak bond. So to make this one strong, to make this solution strong, we are supplying some energy here. So we have to supply the energy to make this one what? Strong here. So endothermic it is. Delta V mixing will be greater than 0 here. Okay. The resulting volume always will be more. Why? Because between these two interactions are less known. When they are having interactions are very less between A and B, they occupy more volume. If they are having strong interactions between A and B, they occupy less volume. The resulting volume will be decreases in that case. But here what happened? Whatever the interactions you are getting here, isn't it? Which are very weak. So we get more volume here. Understood better? Otherwise, I will explain like you see. A and A plus B and B, you are getting delta B, that one AB. Now, where strong interactions are there, beta? Here strong. And here also strong interactions are there. Here, what type of interactions you are having? Weak interactions. Remember, beta, when you have strong interactions, molecules will come together, get together. In that case, what happened? They occupy less value. When they are having strong interactions, the occupied volume will be less. Correct or not? If you are thick friends, you will sit near by near. If you are enemies, you will sit away from each other. Correct or not? Same thing. Interactions are strong here. Interactions are strong here. Then they occupy less value. They occupy what happened? Less value. The interactions are weak here. The interactions are weak here. They occupy what happened? More value. Now delta V is equal to what? V final minus V initial. V final is what? More. V initial is what? Less. So resulting always will be positive only. Positive means what happened? Greater than 0. So delta V mixing always will be greater than 0 when you compare delta and mix. Isn't it? Always will be, both the case always will be greater than 0. The solutions forms minimum boiling azeotropics here. So azeotropics means what happened? Generally when you mix these two solutions, this one 95 ethanol and water you are mixing here. Both are actually what happened? The positive deviation. Non-ideal solution is positive deviation. Now this is 95%, this is 5%. Now this is generally called rectified spirit. If you have 100% of alcohol, that is called what? Absolute spirit. If you have 5% of water, that is called rectified spirit. Now this can be taken as what? Azeotrope with minimum boiling azeotropes. Why? Because the ethanol boiling point is what? Something less than 100 degrees Celsius. Water boiling point is 100 degrees Celsius. Now when you mix these two on, the boiling point will be changes to what? Less than 100 degrees Celsius. Examples for positive deviation, let me see this one. All these are the examples for what? Positive deviation. See, this one is acetone, better. Acetone or propanone, carbon disulfide, again acetone. With what? Alcohol, ethyl alcohol. Ethyl alcohol it is. Acetone with benzene, benzene with CCl4, chloroform with CCl4, water with alcohol. All these comes under what? Positive deviation. Compulsory, you have to remember these examples, right? These are the important examples. If you practice, you will get. Really, if you see what happens, you will get that. Here we see the negative deviation better. Negative deviation. In this solution, solute and solute, solvent-solvent interactions are less when you compare solute-solvent. Okay, whatever the new interactions are getting, they are what? Strong here compared to previous interactions. Isn't it? For example, is something a student is studying in college, something what happened, 10th class is studying, 12th class is studying. Okay, in 12th class what happened? Two students are there. Two students who are there, Parth and Venkatesh are what? Very good friends, Parth and Venkatesh. When they are studying in the 12th class, isn't it? They are very good friends. Very good friends. But when they jump to what happened, something BTech or BSc, whatever it may be, they are now studying what happened in BTech. Now they enter into BTech actually. Now, Parth and Venkatesh, isn't it? They are now, previous they are what? Very good friends. But they enter in, when they enter into BTech, what happened? They got new friends now. Now Parth will friendship with some unknown person, X. And Venkatesh will friendship with what? Some other person, Y here. Now, here, now they become thick friends because they are going to movies also here. Here they will come to regularly school only. After that, they don't meet actually. Here, even after the BTech class also, they are moving to what? Something what happened? Cinemas also. Going to something what happened for something what happened, whatever it may be. Even tours also they are going actually. That means what happened here, when they get what happened, new interactions are here what happened very strong when you compare with what previous interactions. Similarly, solute-solute interactions, solvent-solvent interaction, liquid A interactions, liquid B interactions, which are what? Weak when you compare with what? When you mix here. In that case, what happened? You will get this equation. In that case, what happened? Partial pressure A plus partial pressure B is always lesser than what? P total. Lesser than what? P total. For example, if it is what? 40. This can be for 50. How much you are getting here? 100 you are getting here. So definitely it will be less than here. Correct? Next. These the interactions become stronger and escaping tendency now we don't have escaping tendency. Again, we don't go to what initial state because once we get strong bondings here in the new interactions, they don't go to what previous one. Therefore, escaping tendency will be decreases. Let me take one example here. Acetone, I have taken example. Between acetone and acetone, what type of interactions will be there better? Acetone, what type of interactions will be there? Simply what happened? Chloroform. Are you there? Acetone, what type of interactions will be there? Similarly, chloroform, what type of interactions are there between chloroform and chloroform? Anybody? Surya Sabi
In acetone,
beta.
van der Waals.
In acetone, what happened? We get slightly what happened because here negative charge is there, here positive charge is there. So slightly we get dipole forces, dipole. Here it is positive, here it is negative. Slightly we get here dipole interactions. Slightly dipole interactions. In this case, what happened? Here also we get the dipoles we don't develop definitely because of the electronegativity difference between carbon oxygen is more. This electronegativity is more. Therefore, we get negative positive charges. Negative and positive charges. But here we get definitely will have van der Waals forces. Okay, the van der Waals forces present in where? In the chloroform. Correct? So, but when you mix, what happen? Oxygen and hydrogen, these two can form hydrogen bond. When you mix, what happen? Oxygen from acetone, hydrogen from chloroform can form what type of bonding here? Hydrogen bonding it can form. Now, hydrogen bonding is stronger than van der Waals forces. Hydrogen bonding is stronger than what? This is dipole forces. So definitely strong here. So that is the reason we are getting. After mixing, the two molecules are forming what happened? Strong bonding. Now, because of this, what happened? Delta H will be lesser than, delta V be lesser than 0. Because the interactions, if you observe here, what happened? The interactions, if you observe what happened. I'm saying what happened here. A and A plus BB giving rise to what? AB. In this case, what happened? Weak interactions are weak. Here also what happened? Weak interaction. Here strong interactions are there. When they have strong interactions, value will be what happened? V will be less. Then I mean weak interactions, V will be what here? More. Definitely delta V is equal to V final minus V initial. So V final is less, V initial is more here. So what we get here? Less minus more always will be minus only negative. So negative means what happened? Lesser. Now this will be definitely exothermic reaction. Delta H is equal to negative for this. Delta H is equal to negative. Exothermic reaction. Because they are getting stable. No. Now this is stable. No. Unstable. Whenever you remember better, unstable is converting into stable. They release that energy and become stable in the form of heat. Whenever stable converting unstable does not possible, by applying some energy only, stable will convert into unstable. Reverse process it is. Now this will give maximum boiling azeotropes. That means what happened when you mix this one, HNO3 and H2O. 68% of HNO3, 32% of water. That mixture is called what? Maximum boiling azeotrope, in which what happened? The boiling point will increases. The mixture boiling point, if you observe. Binary mixture which cannot be resolved into components by distillation is called azeotrope. This is a definition. A binary mixture means what happened? Liquid A, liquid B. It's called binary mixture which cannot be resolved into components by distillation. That means what happened? I have taken AB solution. I got AB solution. I got something called hexane and heptane I got. So these two cannot be separated by simple distillation process. They are called azeotropes. Now, a solution which distills without a change in composition at a particular or constant temperature called azeotropic mixture. What is the meaning of azeotropic mixture, beta? Very simple. So solution I have taken, A, B solution I have taken, which distills without a change in the composition at a particular constant temperature, at a given temperature, at a constant temperature, the composition is not changing. When you distill this one, what happened? The composition of A and composition of B will not be changed here. They are called what? Azeotropes. Both definitions you can take. Any definition. Next, vapor pressure curves for solutions showing positive and negative deviations are given below like this. Now, if you observe this, it is also there in the textbook also, beta. Now, first of all, we'll see what happened. Ideal solution. Beta. First of all, we'll see for ideal solution. Then we go to what? Positive and negative deviation. Okay. Now here, only first component is there. Sorry, second component is there. X2 is equal to only here. Second component is there. Okay. Here first component is there. That means here only benzene is there. Here only toluene is there. Like that we can. Now from here to here, if you move to what? From here to here, x-axis, the amount of second component amount, what happened here? Decreasing. Second component amount is what? Decreasing. And first component what? Increasing. Correct or not? Second component is decreasing here. And first component is increasing. Now, definitely the second component is having more amount here. Almost all 100% only second component is there. Therefore, here I am taking the vapor pressure of the second component, P2, the vapor pressure of the second component. Here the first component only is there. So I have taken here the vapor pressure of the first component. Why I have taken below? Because In default, what happened? This second component is having what? More vapor pressure. Okay. When compare here, one what happened? One is having less vapor. For example, just imagine this is what hexane. This one is heptane. Just imagine this one. One is what? You take one is hexane, and second is heptane. Definitely, what happened when you have more molar mass? The vapor pressure will be less here. So hexane is having less molar mass. Therefore, its vapor pressure is what? More actually. So one is having, so reversely I have written. So you take this one as a 2 and this one is a 1 here. Right. Now here will be vapor pressure will be more here. So it is what more. So whatever it may be, okay, whichever is having lesser or higher, leave it that one here. Now here the x1, if you observe what happened, x you are having a 2 now, right? Let me see here what happened. The vapor pressure of the P2 from year to year decreasing or not, correct or not? Tell me better. Is it correct graph or not? The vapor pressure of second one decreasing or not? Tell me better. Is it correct or not? Why it is decreasing? Can anybody say? Why the vapor pressure of second liquid is decreasing? Why it is decreasing better from year to year? Anybody? Why decreasing better? Anybody? According to which law it is decreasing? According to which law it is decreasing better? Because mole fraction is high. 1 it is. So it has high vapor pressure. In second, if you observe, mole fraction is 0. It got 0 vapor pressure. That means I told you already. Second, mole fraction of X2, year to year what happened? Decreasing. When mole fraction of second component is decreasing, its vapor pressure also will decrease here. Now here if you observe, mole fraction of X1 it is, mole fraction of 1 is what? Higher, you got high value. Now here what happened? Mole fraction is decreasing. I'm writing over here. X1, mole fraction is what here? Decreasing. Mole fraction is decreasing. Now you see mole fraction is what here? Decreasing. The mole fraction is decreasing. So from here, when you go from like this, when you go like this, what happened? Mole fraction is decreasing. Okay, when you go like this, mole fraction is decreasing. So both P2 and P1, if you observe, when they move, isn't it, in this direction, mole fraction of X2 decreasing, vapor pressure also decreasing. When you move like this, in this direction, mole fraction of X1 decreasing, therefore what happened? It's a vapor pressure also decreasing, according to Raoult's law. Okay. Now in this case, what happened? When you, how to get the total pressure? Now total pressure is equal to this much. This will show what, wherever if you get, if you want to, if in this point, at this point, there will, at this point what happened? X1 will be something 1 minus X2, right? X1 is equal to 1 minus X2 at this point, or X2 is equal to 1 minus X1. You can take line because X1 plus X2 is equal to how much better? 1 minus. Now at this point, what will be the total pressure? This will be the total pressure. At this point, what will be the total pressure? This will be the total pressure. So this line indicates total vapor pressure. So you are getting a straight line. This should be there. This for the ideal solution. This graph will only for ideal solutions. This graph only for what? Ideal solutions. Now, if it is not ideal solution with a positive deviation, isn't it? If it is what? A positive deviation. If it is a positive deviation, then the graph we are going to get above the normal ideal solution. Here we get, here we get above, at this we get. And here also we get above. The values, if you observe, we are going here also we get above. See, you see here. This is actually ideal. This is actually for ideal. Where you are getting curves beta for positive deviation. This is for ideal actually. So now a straight line for ideals, we are getting like this, straight line for ideals. Correct or not? Right. Now for positive deviation, you are getting lines over what? Ideal solution like this. You are getting like this. Now for negative deviation, now you are getting below here. Below means what happened? Like this. Below means like this. Like this you are getting. Like this. So you see, this is actually ideal behavior. This is the ideal behavior, right? Now you're getting below. This is ideal behavior. You're getting below. This is ideal behavior. You're getting. So these graphs are very simple beta. Don't do any mistakes. If they ask in examination, explain the negative deviation with a suitable graph here. So very simple. You put normal what? Ideal like this. Take ideal like this here. And then put, if it is positive, put above. If it is negative, put below here. Complete shifts. Right? Example for negative deviation, you can take these examples better. All these are what? Negative deviations. Because once they found what happened, the interactions you are getting with more actually. The interactions you are getting what? More. So these are the examples. Acetic acid, this one is what? Can you say what is the name of this one? CH3, CH2, NH2 beta it is. Ethylamine. Acetic acid and ethylamine. Chloroform and acetone. Chloroform and benzene. Chloroform and what? Benzophenone. This one. PHC double bond O. PH. Next. Water and hydrochloric acid. Should we have C here? Here, just here, carbon here. One more carbon here. No. Water and HNO3. Acetone and aniline. Aniline it is. This is for acetone. In all these cases, the new interactions are what? Very strong because of maybe hydrogen bonding in all the cases. Understood beta? This one is about what? Ideal and non-ideal solutions. Now let me get the answer for this one. A binary solution of ethanol and N-heptane is example for what beta? N-heptane ethanol. Anybody? Anybody?
Non-ideal.
Non-ideal, positive deviation. Positive deviation. Why? Because when they mix, right, this can form hydrogen bonding beta. This cannot form, no hydrogen bonding. When they mix also, what happened? Do you get any hydrogen bonding if you mix these two? Tell me beta. If you mix these two, do you get any hydrogen bonding? No. Because it never form hydrogen bonding. Which one? Heptane. So when you mix these two, what type of interactions will be there when you mix here? Van der Waals forces. Van der Waals forces. Now, before mixing, it has hydrogen bonding. Before mixing, ethanol is having hydrogen bonding. After mixing, it is getting van der Waals force. So van der Waals force is weak. So definitely what happened? It will come back into what here? Original force. Right? So what type of force it is? A positive deviation. Whenever what? Before, initial is having more interactions, we get positive deviation. This is about what happened. We completed what? These positive negative deviations we completed.